In the previous video example had a couple of points other than finding roots of a function. The first was to remind you of the quadratic formula. This won't be the last time you'll need it in this class. The second was to get you used to seeing messy answers. In fact, the answers in the above example and that example from the previous video are not really all that messy. However, most students come out of an algebra class very used to seeing only integers and the occasional nice fraction as answers. So here's a fair warning. In this class, I often will intentionally make the answers look messy just to get you out of the habit of always expecting nice answers. In real life, whatever it is, the answer is rarely a simple integer such as 2. In most problems, the answer will be a decimal that came about from a messy fraction and/or an answer that involved radicals. One of the more important ideas about functions is that of the domain and range of a function. In simplest terms, the domain of a function is a set of all values that can be plugged into a function and have the function exist and have a real number for a value. So for the domain, we need to avoid division by 0, square roots of negative numbers, logarithms of 0, and logarithms of negative numbers. If not familiar with logarithms, we're going to take a look at them a little later. The range of a function is simply the set of all possible values that a function can take. Let's find a domain and range of a few functions. So for example 4, we're going to find a domain and range of each of the following functions. So for part A, f of x is equal to 5x minus 3. We know that this is a line and that it's not a horizontal line because the slope is 5 and not 0. This means that this function can take on any value, and so the range is all real numbers. Using mathematical notation, this is the range, which is equal to left parenthesis negative infinity to positive infinity right parenthesis. This is more generally a polynomial, and we know that we can plug any value into a polynomial, and so the domain in this case is also all real numbers. Or we can say that x is going to be in between negative infinity and positive infinity, or we just write that as left parenthesis negative infinity comma infinity right parenthesis. Let's take a look at the next example, part B. G of t is equal to the square root of 4 minus 7t. This is a square root, and we know that square roots are always positive or 0. We know then that the range will go from 0 to infinity. Now, for the domain, we have a little bit of work to do, but not much. We need to make sure that we don't square roots of any negative numbers. So we need to require that what's under the radical is the radicand, which is 4 minus 7t, and it must be greater than or equal to 0. So we're going to solve for t by, we can add 7t to the right side, and then divide both sides by 7. So that means that t is less than or equal to 4 over 7, or we can write it as t is less than or equal to 4 over 7. So the domain is then the following. The domain being t is less than or equal to 4 over 7, or left parenthesis negative infinity comma 4 over 7 with the bracket because we need to include that value because of the equal sign. Part C, it says h of x is equal to negative 2x squared plus 12x plus 5. Here we have a quadratic, which is a polynomial. So we again know that the domain is all real numbers, or in this case, domain is x is in between negative infinity and infinity, or we're going to write that in interval notation, left parenthesis negative infinity, comma infinity parenthesis. In this case, the range requires a little bit of work. From an algebra class, we know that the graph of this will be a parabola that opens down because the coefficient of the x squared is negative. And so the vertex will be the highest point on the graph. If we know the vertex, we can then get the range. The vertex is then x, which is equal to negative 12 in the numerator over 2 times negative 2, which is equal to 3. So we know the value for x is going to be 3, and then we're going to plug 3 in for the value of x to find out what that y is. So we're going to get negative 2 times 3 squared plus 12 times 3 plus 5, which is equal to 23. So the ordered pair is 3, 23. So the 23 is the y value, which is the largest value of that function, which is the maximum. So as discussed, we know that this will be the highest point on the graph or the largest value of the function, and the parabola will take all the values less than this. So the range is then parentheses negative infinity, comma 23 with a bracket. Part D. F of z is equal to the absolute value of z minus 6 minus 3. This function contains an absolute value, and we know that absolute value will be either positive or 0. In this case, the absolute value will be 0 if z is equal to 6. And so the absolute value portion of this function will always be greater than or equal to 0. We are subtracting 3 from the absolute value portion, and so then we know that the range will be the following, bracket negative 3 comma infinity. Now we can plug in any value into an absolute value, and so the domain is once again all real numbers. So we can say left parenthesis negative infinity, comma infinity right parenthesis. Part E. G of x is equal to 8. This function may seem a little tricky at first, but it is actually the easiest one in this set of examples. This is a constant function, and so any value of x that we plug into the function will yield a value of 8. This means that the range is a single value, or the range is just 8. The domain is all real numbers, so it would be left parenthesis negative infinity, comma infinity right parenthesis. In general, determining the range of a function can be somewhat difficult. As long as we restrict ourselves down to simple functions, some of which we looked at in the previous example, finding the range is not too bad, but for most functions it can be a difficult process. Because of the difficulty in finding the range for a lot of functions, we had to keep those in the previous set somewhat simple, which also meant that we couldn't really look at some of the more complicated domain examples that are liable to be important in a calculus course. So let's take a look at another set of functions, only this time we'll look for the domain.